So hello everyone. Today we are going to solve one of the exercises in Atiyah book. So it is exercise 2.20, and let us see how much time it takes me to solve this problem. So we are given a ring homomorphism. Okay, so this is a ring homomorphism. And we are given a flat module. This is a flat A module. Okay, and so we can make M into we can make a new module. So we have this MB, which is given by B tensor AM. So B, the ring B here is not only a B module but also an A module, because we have a restriction of scalars to A. So this tensor B tensor A can be made into a B module. So this is a B module. Okay. So we have to show that MB is flat. Okay. Sorry for not writing complete sentences, but let us go. Okay, so there are multiple ways of showing that a module is flat, and I think the most convenient one would be to show that if we have an injective map between two modules, in this case B modules, then the induced map is also injective. So note that the original module M was A module, but now this new module MB is a B module, and we have to show that it is flat B module. It's a flat B module. Okay. So let us take a map, let's say let's say n prime to n, maybe. Suppose this map is a B module homomorphism. Is a B module homomorphism. Is an injective B module homomorphism. So we now have to show that F, the induced map, let's say it doesn't matter which way I write it, but let's say this thing. MB tensor n prime going to MB tensor n. I need to show that this thing is injective. This map is injective. This map sends an element here in MB. Let's call that X tensor Y to X tensor F of Y. So we have to use the fact that M is a flat A module. So what happens when we tensor MB with n bar? So, and this is a tensor as B module, so let me write B in the subscript, and then MB is B tensor A B tensor M as A modules, but this is so this is both an A module and a B module. So sometimes also called AB bimodule. And I am tensoring it with n prime. And then by one of the results that's proved in Atiyah's book, what we can do is we can write this as, this is say isomorphic as both B and A modules to B tensor AM. This is isomorphic as I think both A and B modules too, and certainly as B modules, these two are isomorphic. But one might wonder why they are isomorphic as A modules. But this is also clear because you can take the same map, same isomorphism, which gives you these two modules as isomorphic as B modules, and you can show that it also it behaves nicely with multiplication by scalars in A. And now we can use one of the results in Atiyah to write it as this thing. Okay. And similarly we can write MP and as an tensor B tensor AM. And kind of like the only thing that remains to show is to check that the map induced by F on okay, so this is the picture. We have map between n prime to n, and then we need to show that this map is injective. But we know that this thing is isomorphic to and bar tensor B, and then this isomorphic to M, and tensor with B tensor with M over A. And we know that there is an isomorphism between these two. Let's call this phi bar maybe, and let's call this phi. And we also have maps between these two. So note that F was a homomorphism between n prime and n. So F tensor 1 is a homomorphism between n prime tensor B and n tensor B. But this is a B module homomorphism. This is a B module homomorphism. So the thing that I'm stuck at right now is to see why this thing is a B module homomorphism. We know that this thing is a B module homomorphism induced by F, but I don't know why this thing is a B module homomorphism. And actually it's technically I don't know whether because like we have, if you have a map going from M to M bar and to N bar, and these are all modules over the same ring, and we have a map F and map G here, then F tensor G is a module given by is a module homomorphism given like this. But the case with us is, so these are, let's say, both A modules, but the case with here is one map F tensor A is a B module homomorphism, but this identity map, this is an A module homomorphism because it's a map between M and M is an A module. And but why is A module homomorphism? So why is, how can we make sense of this thing? Is F tensor A an A module homomorphism? The answer to this is I think it should be it should definitely be yes, but how should I justify it? So now we are multiplying A with some element of n tensor B, but then this thing is n times A dot B, but A dot B, the action of A on B is like this, and so it's a tensor FA times B. So I think I did not mention. No, I did. Like, I'm taking here F as it B module homomorphism, and this thing is also F, and which is kind of confusing. So instead of changing this F, I'm going to change this F to G, and so I will have G here, G here, and a whole lot of other bunch of places. And now so the thing with commutative algebra is like most of the things that you think should work, they work, but it's sometimes just a bit of a hard work to actually prove them, to make sure that they actually work the way you want them to work. Like kind of like housekeeping stuff. So this G tensor A is an A module homomorphism, and then this is also an A module homomorphism. But why G tensor A tensor 1 is also a B module homomorphism? I think because if you have okay, so the only thing that's left is we should somehow show that we have to show that phi bar and phi are such that this diagram commutes, and then we are almost done. But let me go over this again a little bit. So MB tensor N was isomorphic to, was actually equal to M B tensor A M tensor N, and this was isomorphic to N. I to So what's the map? What's the map here? So we are taking a B tensor A M this thing goes to under this isomorphism, and then this thing goes to so let me just reverse the arrows maybe. Okay, let me just give you the main steps. So step 1, so this f is going from n to where, n bar to n. First see that I'm confusing a lot of things here. Sometimes I'm writing FLG and GSF. Okay, let's write F here, and then n bar B to is injected. This is step 1. So F as a P module homomorphism. Well, it's just really simple why this injective, because like this thing is isomorphic to actually n bar, and this thing is isomorphic to n, and we have this map f between them, and then we can map it to here, this to here, where n goes to n tensor b1, and here n bar goes to n bar tensor b1, and this whole diagram commutes. And because this and this are isomorphism, it follows that if f is injective, then this should also be injective. Because like first of all, let's see why this diagram commutes. Because n bar goes to n bar tensor with 1, and then this will go to f of n bar tensor b with 1, and if you take this from here to here, it will go to f of n bar, and then this will go to f of n bar with 1. So this diagram commutes. So because this diagram commutes and f is injective, it follows that f tensor 1 is injective. Because like if you have some element which goes to 0 here, then it will go to 0 here. No, not like this. If you have something here and it goes to 0, and because this map was isomorphism, so there is, suppose n bar tensor b goes to 0, then this thing goes b n bar tensor 1, this thing goes to something which is f of b, this thing tensor 1, but we can take b out, f of n tensor 1, and it means that this thing goes to 0, this thing must also go to 0. This thing must also goes to 0, but this thing by definition goes to sorry, here it should be b n bar, and then this goes to this, and this goes to f of b n bar tensor with 1, which is the same as b f of tensor with 1. And so this thing is 0, but because this thing was this thing is isomorphism, this thing is 0, and this thing was injective, means this thing is 0, and because this thing was an isomorphism, so it means this thing is 0. So this is pretty easy. So what is step 2? Step 2 is G tensor 1 going from M prime tensor B tensor A with M going to N tensor B tensor A. This thing, we claim that this map is also injective. And this map, I claim this map is both an A module and B module homomorphism. Why is it an A module homomorphism? So G tensor 1 was a B module homomorphism, but it is also an A module homomorphism. This is also an A module homomorphism. The reason being here, this above, this thing is an A module homomorphism as well. So this thing is this whole thing is an A module homomorphism, and I think you can prove a general fact, or maybe a lemma, which says that if M is an A module and N is an A B bimodule, and N, let's say N prime, are AB bimodules if F goes from N to N per is an AB bimodule homomorphism, which means that it is an A module homomorphism and also a B module homomorphism. Then F, let's say one tensor F going from M tensor N to M tensor N bar is also an AB bimodule homomorphism. So we already know that if M is an A module and N is an AB bimodule, which is in a consistent way, then M tensor A, M tensor N is both a AB module, which means it's an AB bimodule. And we claim that if we have an AB bimodule homomorphism, then the induced map 1 tensor F is also an AB bimodule homomorphism. Or more generally, I think you can replace this one by G maybe, and M by M prime, and M prime, and G M to M prime is an A module. So what would be the proof? What would the proof look like? So we know that G tensor F is an A module homomorphism. Because G is an A module homomorphism and Fn is an A module homomorphism, then G tensor F is an A module homomorphism. Why is it now B module homomorphism? That shouldn't be too difficult to see as well. Let's take B and M tensor N, and this is G tensor F and M tensor Bn, and this thing is equals to G of M tensor F of Bn. This thing is equals to Gm tensor, because F was a B module homomorphism, we can write it as like this, and then we can take B out. Sorry, I replaced M by N here. Yeah. So I think we're done. So now it's much more clear. So we had a map G going from n power to n, I guess, and then so G was a B module homomorphism. Between this n prime and n, and then what we did was we tensored G like this, and now we can apply lemma. Because the identity map from B to B is identity map is an AB bimodule homomorphism from B to B. Therefore, G tensor 1 is an AB bimodule homomorphism. AB bimodule homomorphism. And now from this we have that tensor A with M, G tensor 1, tensor 1, tensor B, P. Because G G tensor 1 is now an AB bimodule homomorphism, it follows that this thing tensor with the identity map is also an AB bimodule homomorphism. This thing is an AB bimodule homomorphism. Yes. So okay, so because G was injective, we showed in step 1 that G tensor 1 is injective because these things are isomorphic to n prime and because M is flat and G tensor 1 is an A module homomorphism, it follows that the G tensor 1 with tensor again with 1 this is also injective by flatness of M. Okay, and it's injective by flatness of M, and then we know step 3 is that so you can also see this thing here that because MB is a both AB bimodule and the identity map is an AB bimodule homomorphism, then one tensor G is also an it's also AB bimodule homomorphism. So we don't have to worry about anything, and then we have isomorphisms. So here it should be n prime. So here n prime bar B tensor M goes to B tensor A with M one can easily check that this diagram commutes now. And now because this thing is injective, it follows that this thing is also injective. Because these 5 bar and 5 are isomorphisms. So that's where we would end our video.